Hi. In the previous sessions, we have been discussing the Clausius mathematical statement of the second law of thermodynamics, and we have seen that the statement can be broken up into two parts. One applicable for the reversible process, which is known as the Clausius theorem, and the other one applicable to an irreversible process, which is represented by the Clausius inequality. So far we have proved the equality part of the mathematical statement of second law, or the Clausius theorem, in our previous sessions. Now in this particular session we will try to establish the Clausius inequality, which is the second part of the statement. Okay, so let's revisit the statement of the Clausius inequality. So here I have just included the statement for an internally irreversible cycle. For an irreversible cycle, that's what we mean. For an internally irreversible cycle, the closed integral of ratio of heat absorbed by a system to the temperature at which the heat is received is always less than 0. And that's a statement, or mathematically speaking, the closed integral, or the cyclic integral, we can call it a cyclic integral of d bar q over t for an irreversible process should always be less than 0. So that mathematical expression is stated as the closed integral of the ratio of heat, so that is d bar q, ratio of heat, which is d bar q, absorbed by a system to the temperature at which the heat is received, that is T, is always less than 0. So mathematically you can put it as this expression, where d bar q is the amount of heat transferred and T is the temperature at which the heat is received. Now our aim is to prove it. So let's say how to prove this particular mathematical statement. So in order to prove the mathematical statement, so we are considering two reservoirs, two heat reservoirs. Say one is having temperature TH and the other is having temperature TL. So as shown in the slide here. So as usual, let us assume that this reservoir is a hot reservoir and bottom reservoir is a cold reservoir. Or I can just represent that by the fact, let TH be higher than TL. So H denotes the hot and L denotes the cold, okay, or lower, okay, higher and lower, or I could have used the TC also, as we have been using. So it's all up to you, whatever symbol that you are using, right? So lower and higher, or hot and cold, you can take in any manner, right? And in order to make a comparison, I have just taken two engines. One is a reversible engine and the other one is an irreversible engine, as usual. So the reversible engine is represented by R and the irreversible engine is represented by I. And let's compare. So we are going to compare the two engines, and we will establish the Clausius inequality. So you know, the reversible engine will be performing a reversible cycle. So let's assume that the reversible engine, let it be absorbing an amount of heat QH from the high temperature reservoir, does a work W, WR. R denotes that of the reversible, only in order to distinguish it from that of the irreversible one. So let it be doing a work WR reversibly, and the remaining heat that we have represented here as QL be rejected to the low temperature reservoir TL, right? So this heat engine, reversible heat engine, let me say that its efficiency be represented as eta. or I can write as eta R. So eta R denotes the efficiency of this reversible heat engine. And you know what should be eta R equal to? Eta R should be equal to the work output, that is right, W, let me say WR divided by the heat input, that is what, QH. WR by QH, that is okay. Now let me consider the irreversible heat engine, which is also working between the same two reservoirs. Okay, why do we do like this? Because we are going to make a comparison. One is reversible and other is irreversible. Okay, so only to strike a comparison we are doing both, okay, having some same set of values. Okay, most of them having the same set of values. So let us assume that, one more thing, that the irreversible engine is also absorbing the same amount of heat energy QH as that is absorbed by the reversible engine. So let's say that here it is QH, here also it is absorbed. Let us assume that it is absorbing QH, right? And it does a work WI. WI is the work done by the reversible engine, and it will be rejecting an amount of heat is equal to QL irreversible. This I have written IRR. QL irreversible to the low temperature reservoir. Certainly you know that the efficiency of a reversible engine is never equal to the efficiency of a irreversible engine. So even though QH is the same for both I and R, WI and QL are going to be different. W and QL is going to be different for both the engines. Okay, so let's denote the efficiency of the irreversible engine by eta I. And what should be in principle efficiency of that engine? That should be equal to, once again, the work output, that is in this case WI, divided by the heat input, that is again what? QH. That is again QH. Okay. Now let me go to the proof. So these are the notations that we are going to use. So just let's go to the formal proof of the thing. Now let's begin like this. So we know about the Carnot theorem. What is the Carnot theorem saying? Carnot theorem says that the efficiency of a reversible engine like Carnot engine is always greater than the efficiency of any other engine for the same set of reservoirs. Or a Carnot engine operating between two heat reservoirs will be having maximum efficiency. Okay, in whatever way you can say that. So here we have considered R as the reversible engine, or I can consider R is the Carnot engine and I is any other engine which is not reversible. So certainly from Carnot theorem, I can say from Carnot theorem, one thing is for sure, what we can do, eta of the reversible engine, eta R, that is a Carnot engine, eta R will be always greater than eta of irreversible engine, right? So that is where we begin from. Now if this is to be true and you consider the notation that we have used here, I can conclude that directly from our symbols. W reversible, for this to be true, W reversible should be greater than W irreversible. W reversible should be greater than W irreversible. That is clear. Why? Because in our particular example, we have taken QH to be the same in both the cases. Okay, QH to be the same in both the cases. Let both the engines be drawing the same amount of heat energy. That can happen, no problem. Okay, so automatically QH remaining the same, the eta should be directly proportional to the numerator. So eta R proportional to WR, eta I proportional to WI. So since eta R is greater than eta I, the numerator also should be what? Following the same relationship, that is WR work done by the reversible engine should be greater than the work done by the irreversible engine. Not only mathematically, conceptually also that should be correct. That is not the meaning of greater efficiency. So the reversible engine is having greater efficiency. It means that for a given heat input, for a fixed heat input, the reversible engine will be producing more useful work compared to an irreversible one. Okay, so let's take some numerical examples also. I think that also will be helping us to have a better understanding of whatever we are discussing here for an easy comparison. So let me assume for the time being that let 100 joules, okay, so let me say that let 100 joules of heat or 100 some kilocalories of heat, whatever it is, it doesn't matter, be 100 units, let me say 100 units. So here also let that be, that is 100 units, right? Let 100 units of heat be drawn from the high temperature reservoir. Let me say that let the reversible engine be producing say some 40 units of work. Means it is out of 100, it is converting 40 units of heat into work, useful work. And so how much is remaining? By law conservation, 100, 40 has been converted, so 60. So 60 will be just rejected. 60 units, okay, be rejected to the low temperature reservoir. Now let me come to the irreversible engine. So here it's also taking 100 units. Then the efficiency of this irreversible engine should be lesser. So let me say that it's just converting some 25 joules, some 25 joules or 25 units into useful work. So how much is remaining? So remaining is what? 75. So 75 units will be what? Rejected to the low temperature reservoir. So this is a situation actually that we are dealing with, right? This is a situation that we are dealing with. So we have concluded this one. So let me put this one as some equation number 1 or something like that. Okay, so this is my first conclusion, right? Now from this conclusion I can go to another thing also. So can't you directly say that from 1, or it's a straightforward trivial conclusion, from 1 can't you just see that? So if that is the case, what about QL and QL irreversible? QL and QL irreversible. Certainly you can see that QL irreversible should be greater than QL. So I can say QL irreversible IRR, I'm just writing IRR, that should be greater than QL, that is for reversible. QL is for reversible and QL IRR is for irreversible. So let me say that this is a direct consequence. That is my equation number 2. Okay, that also should be clear because greater work is done by the reversible engine, so lesser amount of heat will be rejected to the sink, right? And vice versa. So that is the direct conclusion. We need this one. Now let's consider for the reversible engine. Okay, so let's consider 2 cases. So case 1. We can do this proof in several ways. So this is one of the way in which we can just approach. All these are argumentative. Okay, some logical argumentations. Okay, so case 1. So for the reversible cycle, for the reversible engine, for R cycle, R, okay, for reversible engine R. That's what we're going to do. So let's consider, okay, let's consider the closed integral, okay, of d bar q. We are interested in this mathematical quantity, closed integral of d bar q over t, and we are considering it for the reversible part of the engine. So right, so what should be that one equal to? Means closed integral of d bar q by t means just look at the engine R here. So what are the 2 steps? This is a system actually. R is the engine, or this is the system actually. So when you consider the system, it's receiving heat QH at temperature TH, and it is rejecting QL at temperature TL. Okay, so that is what is happening. So actually, strictly speaking, the temperature, I have to consider this one. Okay, the temperature of this part, I should take this one is some TH minus some DTH. Okay, the temperature of this one is actually should be considered as some TH, which is this temperature TH minus some DTH. But this DTH will be very, very low. Okay, and okay, why should it be like this? Because then only heat will flow from the high temperature reservoir to the low temperature reservoir. But this DTH is pretty small and we neglect it, right? So that we will assume that for this part of the reversible system, the temperature is almost equal to that of the hot reservoir. And if you consider the bottom part means the other part which is in contact with the surroundings. So it is just sending the heat to the low temperature reservoir at TL. So I should say that actually the temperature of the system will be some TL plus some DTL. DTL means very small increment. Why I am taking like this, you can understand. Because then only heat can flow out. Because heat should flow from where to where? High temperature to low temperature. But see, for an internally reversible engine, we assume that this DTL is equal to 0. And we usually do not specify about this DTL values and DTH values in usual cases. But see that exactly actually in a very strict mathematical treatment you have to consider. But leave it, okay? So what you have to do here in order to evaluate this integral, closed integral over d bar q by t, it should be over a complete cycle, right? This circle denotes over the complete cycle. So I can say it should be equal to, in principle, one thing. What is the first part? For the cycle to be complete, I have to consider QH and QL. So let me say that this is QH over TH, the corresponding, okay. So QH over TH, it is receiving temperature, the system is receiving QH amount of heat at a temperature TH, because I have neglected this DTH. So then for the other part, it's not only the system receiving QH, it's also losing QL amount of heat. Remember, we are writing this expression, this closed integral we are writing for the system. Okay, not for the reservoirs. We are considering the system. Our focus is on the system. That should be taken care of. Okay, so this QH by TH, and the system is losing QL amount of heat. Okay, at a temperature what? TL. At a temperature TL. So since the system is losing heat, we have to take the sign as minus. So I am writing minus QL divided by TL. L denotes lower. QL minus TL. I have taken negative because that is our convention. Heat entering the system is taken as positive and heat leaving the system is taken as what? Negative. So that is the thing. Now let me say this is my equation number 3. Okay, right? We have already done this one when we discussed the reversible part of the second law or the Clausius theorem. We have already done it. Okay. Now, but the property for any reversible cycle, but for any reversible cycle or reversible engine, okay, we say cycle or engine, what is this property? QH, we have established this one, QH by QL, QH by QL, that will be equal to what? TH by TL. Okay, this magnitude ratio should be always equal, right? So QH by QL should be equal to TH by TL. Or what you can say, their magnitudes are equal. Or can you rearrange this one and write it? We have seen it during the derivation of our Carnot efficiency. QH by QL is equal to TH by TL. And therefore I can say that QH by TH on rearranging, we have seen this one, right? That is equal to QL by TL. So that is for any reversible cycle. So this is my equation number 4. All right, equation number 4. So just can you club equation 3 and 4? When you club equation 3 and 4, what do you get? So you will get this integral. So these two are equal. That's what equation number 4 says. So that should be cancelling out, and you will get this integral on the left side is equal to 0. Okay, or let me write it here itself. Let me complete it here itself. So 3 and 4 denotes that closed integral or cyclic integral of the quantity d bar q over t should be equal to 0. And remember, this already we have established. I'm just doing it so that there is a continuity. Okay, and this is nothing but the reversible part of the second law of thermodynamics, or the Clausius theorem. Right, now using this argument or using these expressions, we'll be proving the Clausius inequality as well. Okay, so let's go to the next page. I think that'd be better. Okay, so let me do one thing. Yeah. Yes. So we have the diagram here. So the diagram won't be complete. So it's a partial diagram, but you can clearly understand what all things are there. Okay, right. So now we are going to all, you can just assume all the arrows and all. If you want, I can just put it. Okay, so this is QH, this is WR, this is QL, this is QH again, WI, QL irreversible, TH, TL, TH is greater than TL, all those examples, right? Okay, fine. So now we are going to consider the irreversible engine. So for irreversible cycle, for the irreversible cycle, so let's evaluate the same integral. So I'm integrating closed integral or cyclic integral d bar q over t. I'm integrating this quantity for the irreversible part of the cycle or irreversible engine. So let's see what's that equal to. So look at this expression. So you look at the diagram over here and use the corresponding symbols. That's all. Nothing else is there. So what is that? I have to take each heat divided by the temperature. So this is our system now. I is our engine or the system, right? So the system is receiving QH amount of heat at a temperature TH. I told you here it should be TH minus DTH, but minus DTH we are approximating equal to very nearly approaching 0. And this system is losing QL irreversible at a temperature TL. Strictly speaking, TL plus DTL. DTL almost equal to 0. So as far as the system is concerned, I can write it the same way in which we are done. QH, use the sign convention, that's all. Because this is cyclic integral over the complete cycle. That's the meaning. QH divided by TH, that is the same thing, minus QL irreversible. Look at the schematic diagram and write it. Divided by what? TL, the corresponding temperature of the system. TL. QL irreversible by TL. Right? Now that's equal to again what I'm doing is that what is QH by TH? QH by TH. So from the reversible part, you have seen that QH by TH is nothing but equal to QL by TL. Is it not? Just a minute. QH by TH is equal to QL by TL. By TL, right? So you can see that we had given some equation number for that. Yes, QH by TH is equal to QL by TL. That was our equation number 4 over here, right? That's for any reversible cycle, right? So I am replacing with that one, QL by TL. Now minus QL irreversible, let me keep it as such, QL irreversible divided by TL itself. The denominator is same, TL. Is it okay? So this one using equation 4. equation 4 that we have used. Now equal to, you know, the denominators are equal, so that is TL. Can avoid all these steps. I'm just writing it for the sake of completeness. TL minus what? Sorry, QL minus QL irreversible. Now that's equal to, just a moment. Think of the numerator. What you can say about the sign of the numerator? QL minus QL irreversible. Look at the two quantities. Which one will be greater? Will QL be greater or QL irreversible be greater? Hope you remember. We have concluded by taking examples and also by using arguments that QL irreversible will be always greater than QL as far as I is an irreversible engine, because an irreversible engine, for the same heat absorbed, will be rejecting more heat. Means it will be converting lesser amount of heat into work. That's why it is having lesser efficiency. So, and we can just look back. Hope you remember in our previous example, I think it was QL irreversible was something like 75 units, right? So you can see here QL irreversible in our example is 75 units and QL was simply 60 units by following all the rules that we have just discussed so far. So QL irreversible will be always less than QL for the same amount of QH. Okay, for the same amount of QH. Now you can understand that why we have fixed QH to be the same. Then it will be easy for making a judgment or a comparison. For comparison, it's always good that you fix as many quantities as possible, as same for both the systems. So QH is same, so you can just say. So, but, right, QL irreversible is greater than. So what about this one? QL minus QL irreversible will be always negative. That will be negative. So I can say that this quantity will be less than 0. Since, right, or I think that we have given some conclusion, equation 2 or something like that. Let me say that. What is the conclusion? Yeah. Here we have equation 2. We have already concluded in the beginning from Carnot theorem. So using equation number 2. That is there. Using equation 2. Or logically also you can just argument. So therefore I can just say, what is our conclusion? Our conclusion is that on the left side, what do we have? Is not that integral what we have? Cyclic integral or closed integral over irreversible process of d bar q over t. Okay, so let me avoid this equality sign. I should avoid that equality sign, of course. Okay, so that is less than 0. That is less than 0, and is not that we wanted to prove. And this is the inequality. This is the inequality, right? So for an irreversible cycle, the cyclic integral of d bar q over t will be always less than 0. And let's combine it with the reversible part. So combining it with the reversible part, we usually write this one as closed integral of or cyclic integral of d bar q over t is less than or equal to 0. Okay, less than or equal to 0. So you can see that this equality holds good for reversible cycle, equality for reversible cycle, and this less than for what? Irreversible cycle. So be very, very careful that you do not write I or R in the case of this less than or equal to, because that is holding good for both the processes. It's a common case. In many cases or in many authors, okay, many places, this equation is referred to as the Clausius inequality. Okay, and we have been referring to this particular equation as Clausius inequality and the equal to sign as Clausius theorem. Be careful about that. So you can generalize it this way also, because once you understand that the equal sign here in this equation is applicable for the reversible cycle, and less than 0 sign is for the irreversible cycle, nothing wrong in calling this one also as what? Clausius inequality. So both these equations can be referred to as. Whereas this second equation, what you have just discussed here, is nothing but the complete form of the mathematical statement of the second law of thermodynamics. Okay. Now, before we end this proof, let me just make some conclusions. See, what is the conclusion? What actually these equations mean? So, the equation, we are discussing the irreversible only. The equation means, this is the thing what you have written, for an irreversible process of d bar q over t, or t means for the complete cycle, is less than 0. This is the equation. So, the equation means that during an irreversible process, actually the meaning is that there is a net outflow of heat from the system. There is a net outflow of heat from the system. That is actually the meaning, one of the interpretations of what I call the Clausius inequality. The reason you can see that in an irreversible process, you know, irreversible processes are characterized by dissipative agencies. Hope you remember that, right? Dissipative agencies are there. Means energy dissipation will be an integral feature of irreversible processes. So what will happen is that during the cycle of operation, right? So you have got an initial state of the system and you go to the final state of the system, right? That is a forward process, and suppose that you are coming back from final to the initial. Now only the cycle is completed. Is right? Other way of saying is that system was initially at Pi, Vi, Ti. You should always have this one in your background. And the system is finally having Pf, Vf and Tf. That is the final state. So initially the system is taken from this state to this state. Cycle is not complete, please. Okay, Clausius theorem or Clausius inequality do not talk about a single process. It talks about going forward and coming back. Then only you can, okay, that is the meaning of putting this symbol here, this circle. That is why we call it as closed integral, or we call it as what? Cyclic integral. So remember, see, the Clausius inequality and Clausius theorem talks about going forward and coming back. Okay, and then only, so going forward and coming back to the same state can happen in two ways. One, it can happen reversibly, and other, it can happen what? Irreversibly. If it happens reversibly, you know, the system and the surrounding will not have any difference. There won't be any change either in the system or in the surrounding. Then only we can say that the process is reversible. That was our definition of reversible process. And what is an irreversible process? At the commencement, at the completion of the process, means going and coming back. At the completion of the process, if there is a change somewhere, either in the system or in the surrounding, then we cannot call it as reversible, but it is what? Irreversible. And we have seen or concluded that all natural process will be irreversible, and reversible process are only an idealization. Okay, why all natural processes are irreversible? Let me remind you once again. That is because so far we are not able to get rid of or avoid the presence of dissipative agencies like friction, viscosity, turbulence, etc. completely, or magnetic hysteresis. Okay, all these things couldn't be avoided completely. So being this the fact, always remember that the irreversible cycles will always involve certain amount of heat. We are talking in terms of the heat as the energy. Certain amount of heat getting, okay, what that wasted, right? So okay, whenever a system is undergoing an irreversible process cycle, what will happen? Always there will be a net outflow of heat from the system. So when the heat outflow is when it is outflow, not gaining, so you know that that should be some sort of a negative thing, right? And that is why this is less than 0. Okay, that is one interpretation. Or just that is to be very taken care of, that we will come to this one later also. If you talk in terms of the entropy, you know that actually Clausius theorem just happened to be the defining point of the quantity known as entropy. It was through the Clausius theorem we defined the quantity known as what? Entropy. And how did we define entropy? Actually, we didn't define entropy, but instead we defined entropy change, right? So we defined entropy change. Hope you remember that. That was ds is equal to d bar q over t. That was our definition of entropy change. Remember, this entropy change is defined not for, okay, so this definition is not for a cycle. You do not put an integral, closed integral over here and all. Okay, so that is the difference here. So ds is equal to d bar q over t. That is what okay, we have just defined. So for one process there can be an increase in entropy, and for the other process there can be a decrease in entropy as far as the system is concerned. Okay, and this Clausius inequality can be understood. If you want to have a physical interpretation, the entropy of the system can increase or decrease actually. Remember, always be very careful about different statements given in textbooks. See, here I am saying the entropy of the system decreases. I do not say entropy of an isolated system decreases. If anywhere you see the word isolated system, be extra careful. This is a word of caution for all of you. Isolated system. Entropy of an isolated system can never decrease. S is entropy. S of an isolated system can never decrease. Never ever have a statement of the opposite kind. Never decrease. It will always increase or remain the zero. Okay, entropy of, so which is a key word in all these statements. Be very, very careful. I am cautioning you time and again. This is one reason why we will get a lot of misconceptions. So here I am stating entropy of the system decreases. This is the meaning of irreversible process, or the irreversible part of second law. Entropy, I am not talking about isolated system. Entropy of the system, okay, decreases. Means the system is not isolated. It's in contact with the surrounding. That's the meaning. While that can be understood from the next sentence, next part of the sentence or phrase. While that of the surrounding increases. Always remember, there is no any mismatch from the entropy principle. While that of the surrounding increases. So system is there, okay, and the surrounding is there. Whatever is there, surrounding. Okay, so entropy of the system during an irreversible process can get decreased. Why it is getting decreased? Because there is a net outflow of heat from the system. Okay, there is a net outflow of heat from the system, so the entropy of the system will be getting what? Reduced, right? But what will happen? The entropy of the surrounding will be getting increased. S of the surrounding will be getting increased by, this is something very, very significant, by greater amount, such that the change in entropy of the universe is always greater than zero. And that is something very, very noteworthy, such that the change in entropy of the universe is greater than zero. So that is, let me put it like this. So let me say ds or delta s. ds of the universe. What will be ds of the universe? System plus surrounding is what we call as the universe, right? System plus surrounding is what is known as universe. ds of the universe will be equal to ds of the system plus ds of the surrounding. It's always good that you tell about this one here itself. That's what I understand. Okay, ds of the universe will be equal to ds of the system plus ds of the, ds means change, ds of the surrounding, right? So we have seen that in an irreversible process, ds of the system reduces, ds of the system decreases. So I can say here ds of the system is decreasing by a certain amount, you say. But what will happen? ds of the surrounding will be increasing. ds of the surrounding will be getting increased by a greater amount, means in greater magnitude. Okay, so one is negative, you say one is negative and other is positive. Okay, but the positive number is having greater magnitude compared to the negative number. What will happen? The outcome is that ds of the universe will be always greater than zero. ds of the universe will be always greater than zero. What does it mean? The entropy of the universe. Remember, that is a very important statement. The entropy of the universe, S of the universe, will be always increasing in any natural process. In all spontaneous process, entropy of the universe will be going on increasing. Okay, so S increases in all natural process. That is what we call as the principle of increase of entropy, or the entropy principle. We'll also call it as what the entropy principle, or better, we will see that entropy of the universe will be always increasing in all natural processes. And because all natural processes are irreversible in nature. So if you consider the ideal reversible process also, then you can just put it like this. The entropy of the universe will either increase or remain zero. In which case it will remain zero? Only for reversible process. And you know that reversible process is only an idealization. That is a limit. That is the limiting case. Okay. So usually the entropy of the universe, this principle of increase of entropy is usually mathematically represented in this way. So either we'll write ds or delta s. So ds of the universe, it is increasing means what? ds means s final. Okay, so let me just put it like this. ds of the universe is usually greater than or equal to 0. So this is actually known as the principle of increase of entropy. I will just come to this particular statement in another session also, but see that it's always good that I connect it here. Otherwise you may have. So note one thing here that I'm just cautioning you. In the Clausius inequality equation, this is often okay, people will may get confused. I'm not okay bringing in the confusion, but a word of caution. See here, this equation can be, this factor can be seen, integral over d bar q over t, and you will see that this ds is also integral over, so ds is equal to d bar q over t. So people may have a tendency to just write this d bar q over t by ds, right? Okay, but see that this ds is discussed for a single process, and this one is discussed for a cycle. So if you just substitute ds over here, then you may come to a wrong, okay, just thing. So if you substitute it here, never do it like this. So ds, then you will see that this, okay, no, over the cyclic process ds is less than 0. No, okay. See that this equation you see, and you see this equation. See, okay. So we don't talk about this one, please. Don't do this one. Clausius inequality is a separate thing that is used to check whether a given process is reversible or irreversible. So suppose somebody asks you why we both are much about Clausius equality or Clausius inequality. The reason is that by checking whether the Clausius inequality holds good or not, you can determine or you can conclude whether a given process is reversible or irreversible. Okay, if the Clausius inequality do not hold good, then that process is not going to happen. Means if this closed integral or d bar q by t, you are doing some calculation and you are getting closed integral, you are getting, okay, just let me write it here. So closed integral, you are just doing some calculation, and suppose your mathematics is okay and you are getting the result like this for the particular process d bar q by t, you are calculating, you do not get equal to 0, but instead you are getting this is greater than 0. Suppose you are ending up and you repeatedly checked your mathematics, there is nothing wrong in the calculations, and if you get for a theoretical process like this, then you conclude that this is against what? The Clausius inequality, right? This is greater than 0. It can never be greater than 0. It's either less than 0 or at the most equal to 0 for reversible process. Okay, so what you can conclude is that this kind of a process cannot occur in nature. Okay, nature forbids such processes where the Clausius inequality is violated. And from the discussion of Clausius equality and inequality, Clausius got the concept of introducing a mathematical quantity which is named as what? Entropy, which can be defined for every state, and the change in entropy later was found to be a very important quantity which denotes whether a process will occur spontaneously or not. Okay, so that's about the second law of thermodynamics expressed in terms of Clausius inequalities. Always remember it has got two parts. Okay, and one is Clausius theorem and the other one is that inequality part. But sometimes, as I told you, that the complete equation is also known as Clausius inequality. One thing, I have just followed a different approach in proving the Clausius inequality for want of clarity than what is given in your reference textbook. I felt that this treatment will be better because this treatment will be giving you some physical insight, if at all possible, regarding what's the meaning of this equation rather than what is discussed there. Okay, so you are free to follow the other part also if you are trying to, that is a bit more mathematical in nature, but this one is clear, I hope, as far as the proof is concerned. It's always good that, and this is a common type of proof that you will see in many other common lectures. I have just taken it from IIT NPTEL lectures, which I found more useful and more satisfying than the treatment that is followed in our textbook. You can just refer to the treatment that is followed in the textbook. Nothing wrong with it, but we'll have to go for a bit more mathematical arguments. That's all. Okay, so please make notes based on this particular lecture. It's always better, and try to conclude it. We'll be doing some problems in order to understand what is this entropy change, increase, decrease, etc. Hope that will put more light on the equality and inequality. Okay, thank you.